This will probably go for a few minutes anyway. Okay, so we're trying to figure out, we already know it's bounded, so I know where you guys are going. You want to use the high neighbor L theorem. So it really comes down to whether this is closed or not. Okay. So you were starting to explain
Yes.
what your thought was.
So
Could you?
each Cn can be expressed as closed interval of 0 to 1
Mm-hmm.
minus finite or infinite set of open sets,
Yeah.
which are always going to be open.
So this is open, open, open. Exactly. Okay.
So union of all of that is still going to be open.
Right. So you're taking an open set, like this is all open right here.
Mhm.
Right. Okay.
Then if
And that's the complement.
Right.
That's what you're going to say?
Yes.
Yeah, it's the complement of what the CNs are. So each of these CNs is closed. So note, each CN is closed since its complement is, well, what its complement is going to be is it's going to be a union of open intervals and two open rays, which are the rays from minus infinity to 0 and from 1 to infinity, right? So if we take everything to the left, everything to the right, and then these open sets in the center, right? The complement of Cn is a union of open sets, and remember that arbitrary unions are preserved under the open property. So if I have a union of any number of open sets, the result is still open, and therefore the complement, which is Cn, is closed. So, or you could just say each of the Cn's is closed, and closed sets are preserved under infinite intersections. See, I could simply say this is closed, because it's a finite union of closed sets. Each Cn is closed. And now here I'm just doing, I'm sorry, so here I'm doing an infinite intersection of closed sets, right? So that's equivalent, you know, just as an infinite union of open sets is still open, we also proved that in class earlier on that an infinite intersection of closed sets is still closed. So this Cantor set is closed and bounded, therefore it's compact. So the answer is yes. Sorry, Alex, we'll get to you in a second. Since C is closed and bounded. So for a justification, I might say something like C is contained in a neighborhood around the origin of radius 2. Just make an interval like that. So that's the bounded part. And C is an intersection of closed sets. So because of that, it's also closed. Did you have a comment? Or?
Yeah, I was thinking about, instead of looking at this over the whole real line, just looking at it at the interval, closed interval from 0 to 1.
You can do that too.
So that's a compact T4 space.
Compact T4 space, yes.
So then you can just use.
So it's normal, basically. Pardon?
You can just show it's closed.
Right. You could just show that it's closed in that case.
Right.
But I think arguing that it's a compact T4 space, starting with that this is a compact T4 space, you'd have to first of all explain all of that.
Well, I mean, we already know that 0, 1's compact. Right?
Yeah,
That's
we do. We know that.
And any R is T4, and so that any
Right.
subspace is